So thank you very much. So my research was about discovering 3D magnetic turbulence based on single polarization map. This was the work in collaboration with Professor Lazarian from University of Wisconsin Madison and Professor Dmitri Pogosyan from University of Alberta, Canada. The major problem is when we measure interferometer data when studying turbulence, we have to, in the previous studies, we have to analyze an array of different wavelengths. And because of this, it was pretty difficult. It was required to have a lot of measurements for different wavelengths. So, and in our paper, we suggest to introduce a new measure of static turbulence, and it will only have to have only one wavelength instead of the previous studies. So this is how our new measure will look like. Whereas is spectrum, directional spectrum, and we will name our new measure as polarization-angle directional correlation. Numerically, it could be found using like two-dimensional Fourier power spectrum. Both cosine and sine we will determine by Stokes parameters. So why this measure is important? Because it solves the previous problems in the previous literature about angle overlapping, first of all, and also there is robust filtering for our setup. So let's determine our setup. So initially we consider both Faraday rotation emission and the synchrotron emission, and because of the cases when we have too strong magnetic field, Faraday rotation rotates our vector very rapidly, and because of this, we have so-called angle rapid. And because of our new measure, our results show that this problem is unsolved. So this is the description of our setup. So where phi emission is describing the synchrotron emission, and lambda squared rotation measure. Rotation measure is determined by Faraday rotation. Corresponds to Faraday rotation component. So the transition component between the dominance of Faraday rotation and synchrotron emission occurs where the multiplication of lambda squared by sigma Rm, where sigma is variance of rotation measure, has the order of magnitude of 1. Analytically, we're suggesting that for short wavelengths of emission, it will be a synchrotron emission angle dominance, and later, since lambda grows with the square root law, Faraday-screen emission will be dominated in very large lambda situations. So, in general, we used different setups for simulations. We used both synthetic generation of the cube of MHD turbulence, MHD magnetic turbulence, and also we studied both super-Alfvénic and super-Alfvénic turbulence, and those described by collaborators scaling law. We used Asena, and our cube size was 156 to the power of 3 and 512 to the power of 3. And as I mentioned, we studied both super-Alfvénic and super-Alfvénic turbulence. Very known Stokes parameters gives us the transition of both Stokes and Q and Q parameters, as well as polarization angle and intensity. Those results were obtained for synthetic cube that was governed by Kolmogorov -5/3 scale. Projection from three-dimensional chart to two-dimensional chart. And later, when we take Fourier transforms and get energy spectrum, we'll see interesting break for super-Alfvénic turbulence. And the position depends on alpha Mach number, and it also changes for different alpha Mach numbers. The red curve represents our broken slopes that we introduce synthetically, governed by inverse Fourier transforms. Based on Lazarian Pogosyan paper in 2025, it was mentioned that the position of the slopes transitions for different alpha Mach numbers, and for example, for alpha Mach number 18, it completely saturates and it changes over this time. So our new measure will study this. Analyzing the mean magnetic field introduction, when we introduce magnetic field along the line of sight, we see that it doesn't appear, it doesn't change as it was described in analytics. Moreover, it remains consistent even for orders of magnitude too much. Coming back to our analysis of different wavelengths, by changing the wavelengths, we change the dominance of whether it will be like Faraday rotation, like screen will be dominated, or whether synchrotron screen will be dominated as well. And with the increase of lambda, we increase the impact of Faraday rotation screen. So described by this, with increase of lambda, it just transitions for different orders of magnitude, so log scale. So the transition is linear. And on the left side is a plot of directional spectrum versus wave number k, and that is the analysis for different. When we change the power law for density spectrum, we'll see that for very large lambda, which corresponds to dominance of Faraday rotation screen, we see that directional spectrum steepens. And this is very important for observers because by analyzing of their observational data, they could understand whether what screen they analyze right now, whether is it Faraday rotation dominated or whether it's synchrotron dominated regime. And plotting the cross-section wave number versus lambda wavelengths of observable radio astronomy data, we see that this transition is governed based on the analytics fork by this factor, lambda to the power of 4 over gamma minus delta, where gamma and lambda and delta are corresponding power slopes of both magnetic field and density spectrum respectively. And this is the comparison of our PADS introduced measure compared to the other known measures. Based on the Lazarian Pogosyan 2016 paper, it was described was different measures of analyzing the polarization maps, and right now we see that it becomes it shows better correlation with the real both simulational and synthetic data, and the corresponding theory seems to be matching with our initial prediction. So our PADS measure is introduced on the top left. So it has large applications for current observational work, especially in radio astronomy, especially in studying emission turbulence and Faraday rotation maps. And the most important feature is that it enables observers to do the previous analysis with study MHD turbulence with only 5 wavelengths instead of the previous array of wavelengths. Thank you very much.